which is an effort to put together two things that do not really coexist at the moment, spiking and control system. So I don't think I need to explain what I mean by spiking to this audience. But I'd like to ask the question whether we have a theory in engineering to compute and to process and to control spiking signals and systems. And by this, I mean a theory that would acknowledge the mixed nature of spiking. And by mixed nature, I mean that, well, fundamentally, a spiking signal is an analog signal. That is a continuous time signal. But at the same time, it has a very clear digital readout. We can count spikes. And somehow the field of digital signal processing and analog signal processing have become increasingly separated in engineering. And it makes it difficult to handle the specialty of those signals. Now, this is certainly true in the field of control systems. If you go to Wikipedia and read the definition of what a control system is, well, you will recognize control loops and things that regulate thermostat. But then immediately you see this strong separation between what is called continuously modulated control, which is a complicated terminology to mean a regulation process, and typically the regulation of a physical quantity. And then the sharp contrast with anything that has to do with combinational logic or automata. And the world of automata and control systems has become increasingly separated as well. And today, a student or a researcher really has to choose his world, either the physical world of control systems, like mechanical systems, electrical systems, perhaps biophysical systems, or the world of computer science, the world of computation, where we talk, the language is automata. And, you know, I'm always struck by how much students don't connect those two worlds, because they are taught different courses, different languages, and those two worlds have really become separated. So I would say that a spiking theory of control systems for me would be a way to sort of reconcile those two worlds and to reunify those two worlds within a theory that would acknowledge the mixed nature of spiking, which is neither completely digital nor completely analog. It has some features of an automaton and it has some features of a regulated system. Now, I didn't start these questions from scratch, even though I think that this is quite a fundamental question that in all of information engineering today. But I became increasingly interested in that question, studying neuroscience and studying nervous systems. And I would say that in the entire field of neuroscience, there is one person that where I constantly read control questions. It is in the work of Yves Marder, who has been working for more than 40 years on a single network of 30 neurons called the STG, the somatoganglion. And everything is known about the anatomy of that network, about the connectivity of that network, about the neurons of that network. And yet the control of that nervous system is still sort of a mystery. When I read the work of Yves Marder, I see control questions everywhere. And I see a person who thinks of a nervous system as a control system. And then I was invited to Telluride 2 years ago. And this is where I met Gert. And I was fascinated by this workshop because I was fascinated by the similarity between Yves Marder's questions and the questions that were sort of prominent in this workshop, where the challenge is to build those the hardware, the in silico equivalent of those nervous systems. And it is a challenge today to build anything that like an STG in silico, and especially to make it robust to transistor mismatch. So here we are 2 years later. Gert and I have proposed this challenge for the forthcoming Tellurides, and you are very welcome to join the challenge and to join a team of people who is going to try to do that, to control sort of a cartoon model of an STG in silico, and to make it behave a little bit like the STG that has been studied by Yves Marder and many other people. So I think that both these scientific and engineering questions really motivate me in this effort of thinking how much we can think of a spiking system as a control system. And that's going to be the topic of my talk. So I will spend first the first part proposing a concept which I think is central to spiking control systems. And then I will move to something much more concrete, where I will try to explain at a sort of a high level where we stand in building this STG in silico and controlling that STG. And then I hope that to have some times to go back to the question of whether we can make this spiking control theory really algorithmic and computational, because eventually what we hope to do is to have a, to incorporate learning and tuning networks of millions of neurons, and we are not there yet. And if we want to reach that goal, we certainly need to move towards something more computational and more algorithmic. And I think it's all a lot of new and novel exciting challenges, both for control theory and for neuroscience and for neuromorphic engineering. And I'll try to highlight that throughout the talk. By the way, you are very welcome to interrupt me at any time. I probably have too much material to cover, so I don't mind being interrupted and not covering the entire material of the talk. So this is the central picture that I hope you to digest by the end of the talk. And it's, in a sense, an embarrassingly simple block diagram of a control system, the type of block diagram you will see in the first control course, where you try to regulate a plant. And the plant in my talk will be an electrical circuit, so a system that connects a current to a voltage. So it is current driven, and the output, what you measure, is the voltage. And you do that by feedback. And so this is a classical block diagram of a feedback system, where the other part of the system is called the controller. And I've written monotone inside those black boxes. So I will explain later on what I mean by monotone, but monotone is something like sign preserving, so that I can talk about the sign of my feedback loop. And what I want to stress in this talk is that this particular control architecture has a mixture of two feedback loops of opposite sign. So it has one feedback loop that, if you start from here and you draw, it's all positive, it's signs preserving, it's positive, and eventually a negative sign. And so that is a negative feedback loop. And it's sometimes denoted with a dot to mean inhibitory feedback loop in biology. But then there is another parallel feedback loop that starts from here, and you go around the loop, and now you have a minus sign and another minus sign. And so this ends up being a positive feedback loop, or an excitatory feedback loop. And so that's going to be the central motive of this talk. And I sometimes will abbreviate this with a notation like this one. So that will be a sort of a short notation for a mixed feedback control system. Okay, what do we care about mixed feedback system? Well, because the central message of my talk is that this is the key difference between what I would call classical control and mixed feedback control, spiking control. And so what you have on the left here is the first example that you see in any textbooks of control, where what you control is the model of a car that relates force to velocity, which is the mechanical analog of relating current to voltage. And then you close the loop to regulate the speed. And you want to make the speed insensitive to a force disturbance, which could, for instance, model the slope of the road. And if you compare a change in the slope here, a signal, a disturbance, an external disturbance, and the response in open loop and the response in closed loop, you see that the role of the closed loop system is to attenuate the effect of the disturbance. So the negative feedback loop reduces the sensitivity. And that's the fundamental paradigm of control systems, where you use control to reduce the sensitivity of a system to external disturbances. Instead, in mixed feedback, so this is clearly a negative feedback. Okay, so that's, you go monotone, monotone, and then you have eventually a negative sign. So this is a negative feedback loop. But here in the mixed feedback loop, now the current is the current that you would inject in a neuron, and the voltage will be spiking. And this is expressed by the fact that you have the same type of disturbance. In open loop, you have the passive response. And in closed loop, if your disturbance is strong enough, you have this sharp response that is a spike. And so you have, instead of reducing the sensitivity, you have created a form of ultrasensitivity thanks to the mixture of this negative and positive feedback. But it is essentially a negative feedback loop to which you have added a positive feedback loop to create the spike. That's my view of a spiking system. And the whole talk will be about developing that view and seeing how far we can go developing that view. Now, I should say that this mixed feedback concept is a very old one. It is as old as control. But I also have to acknowledge that I heard of the term mixed feedback for the first time after having done control for 15 years. So it's not a sort of a topic that you teach in the first class of control, mostly because it has been forgotten. Now, I was sort of amazed to see that there is a mixed feedback circuit on the cover of what I would call the latest book on control of analog circuits. Now, the latest book is from 1974, just to tell you that it's not an extremely fashionable topic, analog control of nonlinear circuits. But in 1947, for some reason, those authors have decided that this is the circuit that had to feature on the cover. And this circuit is a standard op-amp, where you see that there is a wire from the output to the negative input of the amplifier. That's our negative feedback loop. And then you have the other loop, which is the wire to the positive entry, which is the positive feedback loop. So that is the fundamental prototype of a nonlinear circuit that is mixed. Now, why is this featured on the cover? Because this is a fundamental element that you use to create nonlinear circuits, to create circuits that switches and that oscillate. In fact, it was well known in the 40s, before the negative feedback amplifier became the prototype of control theory. Now, why is this important? Well, here is a very simple model of this device. You can model the op-amp with just a static saturation. Okay, so it has a linear range, and then it very quickly it saturates between 0 and 1. That's typically the characteristic of an op-amp. And then you close the loop, and when you close the loop with negative feedback, you still have an op-amp, but somehow you increase the linear range of the op-amp, and you create something that is less sensitive, that is more analog, that is more tunable. Instead, when you use the positive feedback loop, you convert your op-amp into a switch, into a digital device that has only 1 or 0 at its output, and that possibly has hysteresis. And this is how transistors behave in digital computers. So this is the digital world, the world of switching, the world of memory. And as I said earlier, these two worlds have become separated. But the mixed feedback amplifier is somehow suggesting a very simple device that mixes those two worlds very continuously, because you can go from one world to the other just by strengthening either the negative feedback loop or the positive feedback loop. So you can move between the two worlds continuously. And in between the two worlds, you always have these regions of ultrasensitivity. And that's going to be key to spiking. Now, this is a sort of a cartoon. This is a static model. This is a very simplified model. We want to be more ambitious than that. We want to have models that have dynamics. And in fact, the fundamental reason why spiking is so important, of course, is because of the work of Hodgkin and Huxley. And in the work of Hodgkin and Huxley, you see that same cartoon very clearly. If you know anything about the model of Hodgkin and Huxley, you know that it is the modeled action potential as an RC circuit, so also a nonlinear circuit, same language. And then you have one current that is causing the switching. The sodium is destabilizing the membrane. And you have another current that is repolarizing the neuron, that is the potassium current, that is this tuning slow negative feedback. In fact, you can directly put the Hodgkin-Huxley model in that same feedback loop, where this time my monotone plant is the passive membrane, which is modeled as an RC circuit. And my mixed monotone controller is the sum of these two ion channels, the sodium current and the potassium current. And how do you identify the mixed nature of this mapping? Now, this is a mapping from voltage to current. That mapping from voltage to current is exactly the mapping that was studied through the voltage clamp experiment. And what Hodgkin and Huxley did is they devised an experiment where they were applying a step of voltage and measuring the response in current. This is exactly the input-output characteristics of this block. And what they saw and what they found was strikingly important was the fact that when you apply a positive step of voltage, the response is mixed, is first negative, then positive. And then they separated the role of potassium and sodium, and they saw that indeed the potassium has a very monotone response, always positive, but it is the sodium that has this negative and positive response. So the sodium is a mixed monotone operator, the potassium is a monotone operator. So the Hodgkin-Huxley model fits this mixed feedback model. And now I should add one component, if you want spiking, is that there is a hierarchy between the monotone and the anti-monotone currents. One is fast and localized, the other one is slower and more global. And you need this hierarchy. You need to make the switching local, fast and short range, and the negative feedback long range, global, if you want to get the spike. So the spikes is a fast instability and then a slower repolarization. And that's essential if you want the digital nature of the spike. So it's not a matter of choice, it's forced if you want to be able to count the spikes. So that hierarchy will always be there whenever we talk about this mixed feedback loop. And to finish this first part, I want to define what I mean by monotonicity. So I already indicate that monotonicity is sort of sign preserving. So if I have a resistor I have a monotone function means that if I increase the voltage, I expect the current to increase. That's how we characterize a positive resistor, a nonlinear positive resistor, a nonlinear monotone resistor. But we want to generalize this concept to operators, because when I have a control system, I have dynamical systems. So my input is a signal, my output is a signal. And I want to characterize what monotonicity is as an input-output operator between signals. Now, in circuit theory, there are many ways to generalize the concept of monotonicity, but there is one preferred one in circuit theory, which is passivity. And passivity is a particular concept of positivity where you measure positivity by taking the inner product of the voltage and the current, and that has the dimension of a power, and then you integrate the power over the entire life of the signal. And you say that your device is passive if that quantity is positive. Why is that important? Because that has a fundamental physical interpretation, that it is a device to which you need to supply energy. So if you want to generate a trajectory, you always need to supply energy to the system. So the supplied energy to the system is always positive. In other words, this device doesn't have an internal source of energy. So monotonicity is a mathematical property that sort of characterizes this idea of sign preserving, that I can talk about the sign of my feedback loop, but it's also a fundamental physical property that I'm taking interconnections of monotone device. Now, what is monotone? Passivity is a positivity concept, and monotonicity is a preservation of incremental positivity. So to have the definition of positivity, I need to replace voltage and current by increment of voltage and increment of current. And so this is the mathematical definition of monotonicity that I'm using in my talk, is that I say that an input-output operator between voltage and current is monotone if whenever I increment, I compare two trajectories of voltage, and I compare two trajectories of currents, and I look at the difference of signals, I take their inner product, I integrate, I get a positive quantity. That is the sort of central generalization of this picture, which is the picture of a monotone, of a nonlinear resistor. So monotonicity is the way to characterize how you generalize to dynamical systems and to nonlinear systems the concept of a nonlinear resistor. And that concept was introduced a long time ago. It was introduced in 1960 by Minty, precisely to define to provide a mathematical definition to a nonlinear resistor. 15 years later, that concept became a fundamental concept of convex optimization. When Rockefeller discovered that the gradient of a convex function is always a monotone operator. And from that time on, monotonicity became a central tool for computation. And today, monotonicity is everywhere as a fundamental computational property that is almost a synonym of tractability. So monotonicity is quite important here in the setup of the spiking control system, because we want this picture not just to be conceptual, but we want this picture to be general. Suppose now that I take a current that is not a scalar, but that is a vector. So I take now a network of 1,000 neurons, and my vector of currents is the currents flowing through the 1,000 of neurons, and the vector of voltage is the 1,000 voltages across those neurons. And I built a conductance-based models of that neural network. So I apply the biophysical principle of Hodgkin and Huxley. I connect those neurons with synaptic conductance. The whole system, the whole resulting network still has that exact same feedback structure. It is the feedback interconnection, but this times multi-input, multi-outputs between a monotone operator, and the plant models the passive membranes. So the physical substrate of this, it's almost like modeling a patch of cells. And these operators models all the synaptic conductance and all the intrinsic ion channel conductance that flow in these networks. So there is quite generality in this model. It's not just a model of Hodgkin-Huxley. It's not just a model of one spiking neuron. It is the model of any nonlinear electrical model made of port interconnections of monotone current sources, which is the fundamental modeling principle of biophysical neuronal models. So just to summarize this first part, I took some time to define the setup, but the setup is really meant to think of the most complicated models of biophysical neurons as close as possible to the conventional description of a control system. And the key difference between the two is that I would say that monotonicity is a very central assumption in classical control to talk about negative feedback loop. And we can really think of spiking control systems as adding to this fundamental negative feedback loop, adding some positive feedback loops through the negative conductance. So it's something very simple that you find in every negative resistance circuit, but that has really the generality of modeling all what we can model with electrical models in biophysics. Okay, I don't know whether there are any questions at this point. But this is the first part of the talk. Now, in the second part of the talk, I'd like to go down to earth and to, okay, I have spent some time setting up the scene, sort of a very general framework, but how does that translate to control and STG? Now, this is the topic of a monograph that we are trying to finish, and that is sort of summarizing 10 years of work with my colleagues, Guillaume Drillon and Alessio Franchi. By the way, we are giving a graduate course out of this monograph in June, just before Telluride. And so, yeah, welcome to register if you would like to hear more about this. And we really try to discuss in this book how to control spiking systems, mimicking how we would control conventional control systems. After all, control theory started from electrical circuits. So it's very, the language of control theory is very close to the language of circuit theory. And here we have to add these negative conductance devices to move from classical electrical circuits, passive circuits, to spiking networks. So in that book, the picture is the same as the one that I had described. So I had the classical block diagram of a plant and a controller, and the plant is the passive membrane. So it is a monotone RC network. And the controller is a bank of parallel mixed monotone current sources. And everything that is monotone in the controller models a sort of a fading memory resistor. And anything that is mixed monotone in the controller, that is the difference of two monotone, models a negative resistance device. Okay. Now, if I go back to the simplest spiking system, I can build such a device with just two terms is my controller, one for the negative feedback and one for the positive feedback. So I just need two conductance, like the sodium and the potassium conductance in Hodgkin-Huxley. And I'm going to use as parameters of my controllers the maximal conductance, so the maximal gains of these currents. And this fits very well the neuroscience, the neuromodulation, because neuromodulators can be modeled as modulating the maximal conductance of synaptic currents and ion channels. And so you end up having a control system with two parameters, the parameter of the positive feedback and the parameter of the negative feedback. And it cannot be too difficult to control a system with two parameters. This is like PI control, proportional integral control in classical control. And you do that by hand once you understand the meaning of proportional and the meaning of integral. Likewise, we can do that here because by now we understood that the meaning of positive feedback is to generate the spike, the threshold, and the meaning of negative feedback is to regulate. And so by balancing those two parameters, we can very easily adjust the thresholds. Adjust the threshold is adjusting above which amplitudes I will generate a spike. And of course, I can also shape the spike event. The spike event is perhaps the refractory period. It's the duration of the spike. And you can imagine that you can tune that to some degree with the maximal conductance. So I'm going to think of a spiking, of an elementary spiking system as a very simple control system where I use two parameters to adjust the threshold and the refractoriness. So I adjust the threshold and I adjust the duration of the spike. And that's elementary. You almost don't need a theory. When you can do a little bit of theory, you can do some phase space analysis, but this is all very classical. The question that we want to address is why is that relevant if I want to control an STG? And that sort of question is, in fact, not too unusual for a control theorist, because it is said that more than 99% of industrial plants are controlled with PI controllers, tuned independently of each other. So somehow we know that we can control very complex control systems with PI control, provided that there is some sort of hierarchy between the systems that we control and that we can we know what we tune when we touch a particular PI. Well, what I've learned over the last 10 years is that you can go a long way tuning a spiking system if you want to tune an STG. And that's what I would like to illustrate in the next 10 minutes. So the STG looks like not an easy plant. It is made of about 30 neurons. And if you look at the signals of some of those neurons, you see that those signals are not trivial. Indeed, they are made of spikes, but spikes of very different types. There are bursts so it's not very clear how you go from the elementary spiking system that I've taught so far to that sort of system. But in fact, if you go to the Scholarpedia page about the STG, you see that there is a lot of hierarchy in the phenomenology of that system. First of all, the reason why people got interested in that particular system is that it's because it's essentially the interaction between two rhythms, one called the pyloric rhythm and the other one called the gastric mill. One rhythm is fast, 1 hertz, and mostly continuous. The other one is sort of intermittent and it's much slower. And those two rhythms sort of interact in a very complex way. So this is a feature of the slow rhythm, the gastric mill, and whereas this is a feature of the fast rhythm. And you see that when the slow rhythm is off, you only see the fast rhythm. And when the slow rhythm is on, you see sort of a mixture of the fast and the slow rhythm. And the whole question that Yves Marder is trying to understand is, what does regulate? What does make the system so reliable, even though the individual neurons exhibit a lot of variability, and how is this system so robust? Well, when you dig into what is the pyloric rhythm and what is the gastric mill, you see that those are two prototype of CPG, central pattern generators, and they can be sort of modeled as by the most simple, the simplest CPG, which is just the inhibitory interaction between two bursting neurons. That's called a half center oscillator. That is a model that has been studied for a century. So we can understand the STG as an interaction between two half center oscillators. And then we can understand the half center oscillator as an interaction between two bursting neurons. And then perhaps we can understand a bursting neuron as an interaction between two spikers. And now we have created a hierarchy from the single spiker to the full STG. Once you have figured that out, it's very easy to sort of go back. And indeed, if you analyze the controller of a burster, you do a voltage clamp experiment, and what do you see is that the response is indeed the superposition of two spikers. It is the superposition of one spiker, which is very much the voltage clamp response of Hodgkin-Huxley, and then another one that is sort of slower. And so it's really the parallel connection of two spikers. So if you know how to tune one spiker, you know how to tune two spikers, and now you can try to tune the two together to create the burst. Now, what do you want to create? Again, you want to create a spiking system. What is a spiking system? It is a system that has a threshold, that is an automaton between two events. And the new event that you want to create with the rebound bursters is that when you inhibit the burster, for small inhibition, it has a passive response. For strong inhibition, it responds with a burst. That's called a rebound burst. And that's the fundamental input-output property that will be instrumental for the half-center oscillator. And now what I'm saying is that if you have succeeded in tuning one spiker with two parameters, it's very easy to use the other two parameters to tune the rebound burster. So the problem of tuning the rebound burster is not more complicated once you see in this way than the problem of tuning the spiker. And in the same way, you are going to use the balance between parameters to tune a threshold, but it's a different threshold than the spiking threshold. It is the bursting threshold. You are going to regulate the burst events. How many spikes do you want? How long? Perhaps you want several bursts, so you could shape the events. And then you want to create sort of a mean input-output characteristic. Once you have done that, you have the elements to create your HCO. Because an HCO is a very clear outcome of the rebound spiker. What happens is that one neuron bursts, it creates inhibition in the other neurons, and then therefore it creates a rebound burst. So a half-center oscillator, and in fact any central pattern generator, is built upon that mechanism. Now, what does it mean to tune an HCO? Again, you want to think of your HCO as a spiking control system. That is, as an input-output system that has a switch, that has a threshold, and that gives an automaton between two different states. One state here is that the two neurons don't talk to each other. The other state is that there is the ring that is on. How do you trigger the transition from one state to the other? By inhibition. And what do you have to tune this time? One threshold. How strong inhibition do you need to go from the off to the on? How long do you want the rhythmic event to last? How do you want to tune the duty cycle of that event? You see, again, exactly the same type of question. And this time you are going to use your three synaptic conductance to do that tuning. So you see that when you make this tuning hierarchical, at each step, the level of difficulty of the tuning is exactly the same. It's always about balancing a positive and negative feedback to get a threshold, and then using the negative feedback to tune the event. So it is always like regulating an automaton. The positive feedback creates an automaton, and the negative feedback regulates the automaton. And once you have understood how to tune an HCO, you can tune two HCO. So first you disconnect them, and you have a fast one and a slow one. And then you interconnect them. And very quickly you realize that you can easily create a switch where the slow rhythm is on and then the slow rhythm is off. Again, by doing that, you have defined your inputs, and you have defined a new automaton, a new threshold, and a new event. But as you move on, as you move up, you can make this more and more complex. Already with this 5 neuron network, which is the network that we want to build at Telluride, you can create all sorts of combination between the slow rhythm and the fast rhythm. Meaning that you can create 1, 2, 3, 4, 5 different automata. And each of these automata can be regulated to a different rhythm. And you can go from one automaton to the other automaton just by controlling individual neurons, just by inhibiting individual neuron or several neurons. The control neurons on the left are those circled in orange. And this is what neuromodulation does. And this is why neuromodulation gives you a realm of controllability on a network where you can reconfigure a combinatorial number of automata, and each of these automata can sort of be tuned almost independently. And it's fascinating. I think it works too well to be completely wrong. When we do that in simulation, you know, each neuron has about 10 states. So it's a differential equation of order 10 with 20 parameters. And when you tune 5 neurons, you get 50 states, you get 50 differential equations, non-linear differential equation, perhaps 200 parameters. If you try to tune that from scratch, it's completely intractable. If you tune it hierarchically, it's incredibly robust, it's incredibly intuitive, it works. Moreover, it's very consistent with the scientific observation. All what I have read so far about the scientific observations of Yves Marder are perfectly consistent with this hierarchical control. And it's not to say that the overall system is simple. I think the overall system is incredibly complex. But it is incredibly complex because of neuromodulation. And my claim is that neuromodulation gives you sort of the way of generating all these automata. But it never destroys the rhythm. It never destroys the cells. It never destroys the hierarchy of rhythm. And that's very much how a power plant can be controlled with PID control. You see, you don't want to mess up when you control a power plant with PID control, and you need to make sure that each PI loop has a very specific role and will not interact in a bad way with other PI loops. But if you draw the block diagram of a power plant, you have something very comparable to this block diagram of the STG. So I think that this analogy between PI control and spiking control is in fact very useful, and is sort of something that I've learned from trying to understand the STG. And it has been a long journey because if you start from the view of STG as a dynamical system of order 100 with 200 parameters, it's very, very difficult to find the right angle of attack. And that leads me to the last part of my talk, where I would like to talk about moving towards something more computational, more algorithmic, and how to scale up these principles. Because in the end, PI is not the end of control theory. If you do control theory, probably you like the more advanced concept of control theory. And in particular, state space methods were developed precisely to make classical control more quantitative, to quantify robustness, to quantify optimality, to make the design of controllers more computational. And so the question is there any hope to do that, to do something similar when we build in silico spiking networks of 100 or 1,000 or 1,000,000 neurons, right? And clearly we have to acknowledge that if we use a state space representation, so if we model these neurons with differential equations, the dimension of the state space grows very rapidly. So it's really a large scale system. And so we need a computational framework to, on top of this hierarchical control architecture, which I think is key, but needs to be supplemented with a computational framework. And so it is here that I'm going back now to this concept of monotonicity, which I think is key. And the reason is that if you look at how control theory has become computational, it is precisely by exploiting that concept. You see, the fundamental property of monotonicity is that monotonicity is preserved by negative feedback. So if you ask perhaps the most fundamental question of control theory, which is if my plant has a property, if my controller has a property, what should that property be if I want the feedback loop to have the same property? Well, the short answer is monotonicity. And monotonicity is really the essence of computational control theory. And it can be generalized, and the generalization is called dissipativity theory. But it's really, dissipativity theory really started in passivity and in that concept of a property that is preserved by negative feedback. So in classical control, if your plant is monotone and if your controller is monotone, your feedback system is also monotone. Why is that important? Because as I said earlier, monotonicity is almost a synonym of convexity. And so it's almost a synonym of tractability. So whenever a tractable computational problem is minimizing a convex function, that is equivalent to finding the zero of a monotone operator. So every problem that you can turn in zero finding of a monotone operator is tractable. Well, that's exactly how you make control theory computational. Suppose that you want to to compute just the solution, the feedback solution. If I choose a current V, I, how do I compute the output V? Well, you write your feedback equation, and you want to find V star for I star. Well, this is exactly a zero finding problem for a monotone operator. What is this monotone operator? It is the inverse of the plant, and monotonicity is preserved by inversion, plus a monotone, and the sum of monotone is monotone, minus a constant. So this is one example of a problem that can be turned into a tractable question because of monotonicity. And now you can say, well, I would say that in the end, every question that is algorithmic in classical control can be rephrased as zero finding of a monotone operator. So the real challenge that we want to address now is there any hope to do something similar if I have mixed monotonicity, if I have mixed feedback? So suppose that I try to solve the same question. I try to solve the input-output of this feedback system. And I know that it could be very complicated. The output could be a spiking signal. Well, I do the same calculation, and the only difference now is that the term here, the controller, is the difference of two monotone operators. It's mixed monotone. So this time, if I want to make this problem computational, I have to find the zero of a difference of monotone operators. That's how I can go from conventional control to mixed control. Well, there is an analog of that in optimization, which is, okay, I know how to minimize a convex function. How can I minimize a difference of convex function? And there is a whole industry of algorithms to do that. And in fact, it works incredibly well. It doesn't work well in general, but it works well because of the hierarchy that I have constantly underlined, that we should think of our spiking systems as a realm of monotone systems, and then a few negative conductance that are inserted in the feedback loop with only one purpose, to create thresholds. And somehow, whenever you insert a negative conductance, you are creating a difference of convex function. And the picture that I want you to go back home with is this one, is that what we have on the left is conventional control design, where in the end, everything is like convex optimization, because we are designing systems that are fading. So if you perturb the system, it always goes back to the equilibrium. But we precisely want to leave this world. That's why we design spiking systems in the first place. We want to collocate processing and memory. And we create mixed feedback. And whenever you add a negative conductance in your design, you are creating one bump. And by creating one bump, you are creating the possibility of a memory. If you do that in a non-disciplined way, in a non-hierarchical way, you end up with a function with plenty of local minima, very ugly, very intractable. But if you do that in a disciplined way, in a hierarchical way, it works very, very well. And you really have a path to move from classical control to spiking control in a very, very continuous manner. And that's what I think is exciting for the possibility that, you know, perhaps the gap between spiking control systems and conventional control systems is not that big as it looks. And perhaps there is a way to generalize classical control towards a real theory of spiking control systems, where we control very tightly where we put the memory, where we put the thresholds, but we leverage the whole computational framework of learning and adapting and controlling with conventional control. So I will finish with this. That's my proposal, to develop a theory for computing, processing, and with spiking signals, is to sort of leverage, first of all, to acknowledge that mixed feedback is central to acknowledge the mixed nature of spiking. The mixed feedback amplifier that I explained at the very beginning, that gives you this sort of continuum between the digital world and the analog world. I don't know of another mechanism to do that. So I think we have no choice than acknowledging the mixed feedback nature of spiking. But I think there is hope in thinking of these mixed feedback systems as a feedback interconnection of a monotone plant with a mixed monotone controller, especially when we control where we place the negative conductance, and where we place the negative conductance with the only purpose of creating thresholds. Why do we create thresholds? to have an automaton. Why do we need automata? Because analog computing is unrobust. So we want the robustness, the countability of digital, but we want the tunability of analog. That's really what we are after in spiking control systems. And I think that there is a big hope of moving forward with the concept of mixed monotonicity, which I think is a very classical concept and a very important concept that connects the physical world and the computational world. The physical world, because the monotonicity property is a fundamental property, is fundamentally the property that defines what a nonlinear resistor is. And computational, because monotonicity is a synonym of tractability, that is solvability by context optimization. And with this, I'd like to conclude. Thank you.
Thank you for the exciting talk, Rodolphe. We have maybe 5-10 minutes for questions, so please either directly ask Rodolphe or you can put it in the chat and I will read them. If there are any questions?
Yeah, I have a question. So I thought it was a really fascinating talk. One question that I had, though, was that when we analyze these larger neural systems and when they're doing information processing, we seem to be able to get away with essentially replacing the spiking with rate activity. And we seem to be able to do all right, although there are big clues that the spiking is actually providing some key computational advantages. For example, there will be systems that seem to really prefer synchrony in certain modes. So I'm just wondering what your framework would say about why we seem to get away with forgetting about spiking, and how we can actually find the weaknesses of our current perspective in light of your work.
Yeah, that's a very cool question. Thank you. Yeah. Even in neuroscience, I think this question is still very much alive. Does the spike matter?
Exactly, yeah.
And you have two schools. You have one school who thinks that the spikes is irrelevant. There is this nice paper called The Requiem for the Spike, which I find is interesting. And then you have other people who say, no, every spike is very important. And usually when there is a split of the community between two schools, it means that both are correct. And that's my view, is that sometimes the spikes matters, sometimes the spike doesn't matter. And I didn't spend a lot of time on the third bullet here, but the mean input-output characteristics is precisely the rate characteristic. If I apply a current and I look at the average voltage, I will have a rate curve like this one. Okay? That rate curve is monotone. And this means that sometimes when you have a network, you don't want to think of each node of the network as a spiking neuron or as a bursting neuron. Sometimes you would like to simplify it as an amplifier, as a saturation, as a monotone device. It's all fine. It's all fine at a certain scale. So I think there is nothing wrong about the rate assumption. It is just a simplification. And it's just that sometimes this simplification is fine, but there is a lot that we are missing by making that simplification always. And so everything that has to do with rhythm really cares about the spikes and not just the rate. And so when you have, if you think that, okay, something like this one, the fact that you sort of change the connectivity of a network just by modulating the individual neuron, I don't have a theory to do the same thing with rate models at the moment. And I think that the fact that the event is sometimes a spike and sometimes a burst is very important. So one way to think of such a network as a rate model would be that it is a rate model, but in fact it is several rate models. There is one rate model that corresponds to the spiking model. There is another rate model that corresponds to the bursting model. And the fact that those neurons sometimes spike, sometimes burst, it's like they were changing their rate characteristic. So what I would say is that there is nothing wrong about rate models. I think rate models fit perfectly the picture that I try to propose today, but there is more to it. And I think that the rhythmic nature of spiking is very important and offers a lot of possibilities that are sort of not fully exploited with rate models.
Cool.
Does that answer your question?
I think to some extent, yeah.
There's a question from Miroslav. Can you please ask directly, Rodolphe?
Hi, Rodolphe.
Hi, Miroslav.
I could watch these talks 5, 10 times and always learn something new. And once I've stopped learning new, I'm going to be prompted into thinking new. You know, I can't help but get reminded of something that I remember you having done maybe 10 years ago and presenting a masterful talk at one of our conferences, which was on stabilizing the ping pong ball. And as I recall, it was by timing only, not by modulating force, but only modulating the time.
Oh, yeah.
So I see you, that was hybrid stuff, hybrid systems. I see you now operating at the verge of hybrid, but you're still continuous here, as far as I can understand. So could you see possibly developing a control or an altitude stabilization solution for that ping pong ball problem using spiking, and perhaps spiking will become a part of the plant rather than just an input signal. And I'm asking you this question because I would like to understand spiking in function of solving some mechanical control problem, as it serves in many neuromotor applications, I presume.
Right. Okay, that's a tough question, as always, from Miroslav. But you see, okay, there is something fundamental to the spike, is that you can count the spike. Now, if you can count the spike, it means that you can, anything that is digital, anything that is multi-rate can be implemented with spike. And so anything that has to do with vibrational control can be implemented with spikes. Anything that has to do with averaging can, in principle, be implemented with spikes. And that's why, which is a nice complement to the previous question, because if you stick to rate models, you miss all these opportunities. And we know in control how much you can exploit and how much it has been exploited. Multi-rate IDs, multi-sampling, oversampling, undersampling, all of that is available within the framework of spiking. However, I don't think that spiking can be reduced to multi-rate control. And the additional feature of spiking is really the threshold. The threshold that is always this automaton. Every spiking system has two discrete states. For spiking, it is the equilibrium state or the spiking state. But it could be the equilibrium state or the bursting state, or it could be transition from the spiking state to the bursting state. Those automata are sort of internal states, are sort of and there is a continuum of them. So the automaton is there, but because of the regulation, you can have almost a continuum of the automaton. And so I really think that, yeah, again, if I go back to this STG, what is fascinating in the STG, in this network, is the fact that because of spiking, because of this threshold, you seem to take full advantage of the STG as an automaton, and at the same time, you seem to take full advantage of the STG as a continuous time system. Yeah, I don't know whether it answered your question, but I really think of this this mixed feedback as something that connects the two worlds. Now, everything that exists in each of the worlds also exists there, but I think there is more due to the continuous transition between the two worlds.
No, in the first two sentences you already answered, and more, even getting to averaging and so on. And when you mention averaging, then I'm reminded of singular perturbations, and I'm thinking how a joint friend of ours, you know who I'm talking about, the singular perturbation god, would be seeing multiple time scales in these spikes. Right?
Okay, so I didn't talk about state space models in a single slide today, but the work that we have done for the past 10 years is all in state space, and it's all using multiple time scales, and it's all using singular perturbation theory. So if you want to approach those systems through a state space formalism, which of course is the classical way to do it in neurodynamics and so on, of course, you make a very heavy use of those analysis tools. But I wanted to take the input-output perspective that I emphasized today was on purpose, to say that I think it is a time to go back to the theory of electrical circuits and to think of those devices as input-outputs, because this is really how they become tractable when you want to scale up.
Thank you.
There's a question in the chat about if you are aware of a more robust control mechanisms in the brain or nervous systems different from the mixed feedback that you're proposing. Are you aware of?
Well, first of all, I don't know of another mechanism, but I like the fact that there is more robust, because the one thing that I love about mixed feedback is its robustness. You see, I haven't spoken at all how you model these monotone conductance, and there would be a lot to say, but I think there is a lot of inherent robustness to the mixed feedback principle, because if what you want to achieve is ultrasensitivity, okay, maybe I should go back to the very first cartoon. See, to me, the threshold is here. The threshold is here in the sense that this is the regime where a very fine change in the input causes an event in the output. And I think that is what's, in the end, what is so important in spiking. That's what beats the fragility of analog computing. But that particular phenomenon is highly fragile. You see, you need a very fine balance of the positive and negative feedback to get this ultrasensitivity. So you will never get it if you have uncertainty. And the miracle is that when you make one loop fast and the other one loop slow, there is always a regime in the time domain and in the frequency domain where you will have the singularity. So somehow it's like, you know, you want to create a bump, and how can you be more robust than by saying that I give you a positive bump, I give you a negative bump, and then I tell you the negative bump is sharp, the positive bump is shallow, and now you can play with the amplitude. That's my control parameters. And in the end, I want to create one Mexican hat. It's very robust. You can have a lot of uncertainty about the shape of the bump and so on. But somehow this particular combination always creates the ultrasensitivity. So honestly, I don't know of any other mechanism, and I would be very surprised to find a mechanism that would be even more robust. But it would be fascinating, yeah.
So we have time for one more questions.
If I may, Rodolphe, so this is fantastic work. So, and you touched upon Eve Marder's work, right? The message that she's bringing to us adds one more dimension, which you touched on just briefly, but I think is a very important one in robustness of to variation in parameters, and where she showed that the same behavior can be explained with totally different networks.
Right.
Right, and there's a question of complexity and how do you handle this, and so you brought up the example of we have 16 neurons for Telluride, right? So we can configure it in multiple ways to give the same dynamics, and which is the correct one or which one is the more preferred one, right?
Yeah, that's really what I've learned from her work. That the more I think of the controller as a bank of conductance. And then when I talk about design, you only need 2 if you want to create a spiking. But neurons that spike don't have 2, they have 10. They have plenty of different ion channels. And so they don't tune the balance between just 2, they tune the balance between 10. And so there are lots of ways to achieve the same balance if you are given 10 parameters, out of which 2 are negative and 8 are positive. There are lots of ways to create a 0 by balancing those parameters. And in the end, the only thing that matters for spiking is to create the 0 conductance. And so that's, to me, the source of how variability can coexist with reliability. And that's why I insisted when I was talking about tuning and STG, tuning and HCO, that the only thing that makes this system reliable is the threshold, is when do I switch from rest to rhythm. And I don't care whether this is done by which combination of parameters. I know that I have plenty of positive parameters and I have a few negative parameters. And I will always find a balance that can adjust them. So there is a lot of redundancy indeed, and there is a lot of equal values of parameters that will lead to the same input-output behavior. Now, if you think of those as dynamical systems, and if you look at the attractors of those dynamical systems, they will all be different. And that is the contrast you see that you all very often see in neuroscience in experiments, that you see that an experiment is very reliable, and then suddenly another experiment exhibits a lot of variability. And you always ask, but how comes that this incredible variability can coexist with this? So over-parameterization, make your neural controller, make the bank of filters huge, and you will facilitate the tuning. But you will not make it intractable, provided that you keep the hierarchy. The hierarchy is always there. That's my view. I still think that Eve would say that in nature, it's far more complicated than what I'm saying. But at least as engineers, we always have to simplify, don't we?
All right, thank you. So thank you, everyone. I think we're going to close down now. So the talk will be available soon online. And next week we have another talk next week. So also the same time from another speaker from Europe, also on neuromorphic topics. So thank you, everyone. Thanks again, Rodolphe. And we'll see you next week.
Thank
Bye-bye.
you. Yes.